Hello, Matthews, Gatos here. So we're going to do part 2 of applications of max-min, and we are going to look at ones where we have a set formula to use. So let's look at the very first one. We have an open top cylinder. Okay, that means there's no top. That has copper sides that cost $5.40 per meter squared and a steel bottom that costs $2 per, that should also be meters squared. Find the dimensions of a 10 pi meter cubed cylinder that has the least cost. Okay, so we're looking at a minimum cost. So I have two formulas here. I have a volume, 10 pi equals pi r squared h. And then I have a cost formula. So I want the minimum cost. So the minimum cost is dealing with the surface area. So we don't have a top, we only have a bottom. So we have pi r squared plus, and then this middle section, the lateral area, is found by doing 2 pi r, which is the circumference, multiplied by the height. Now, because this is a cost, I have sides that cost $5.40. So I'm going to take this and multiply it by $5.40. And then I'm going to take my bottom circle, and the bottom costs $2 per meter squared. Okay, so let's just simplify this a little bit more. So minimum cost is equal to 2 pi r squared plus 2 times 5.4, 10.8 pi r h. Okay, so remember I said that the equation that has a minimum is your derivative equation, and your equation that doesn't have a minimum is your isolating equation. So this derivative equation here is only allowed one variable. So you see they both have r's, both parts have r's, but there's this h here, and that's a bit of a problem. So I'm going to use my isolating formula to get h by itself and then substitute that into my derivative equation. So over here, I'm going to divide both sides by pi r squared to get height all by itself. So in doing so, I can cancel my pi's. I have 10 over r squared equals to h. So now that I've isolated height, I'm going to put that into my minimum equation. So minimum equation is 2 pi r squared plus 10.8 pi r times by height, which is 10 over r squared. So my minimum equation altogether, just tidying it up a little bit, is 10.8 times 10, so that's 108 pi, and then r divided by r squared is 1 over r, or r to the negative 1. Okay, so now that I've got my derivative equation simplified with one variable, I'm ready to take the first derivative. Okay, so the first derivative is 2 pi times, bring the 2 down, decrease my exponent by 1, minus, bring the exponent down, which is a negative 1, and decrease that by 1. So I just want to factor this using the greatest common factor. So greatest common factor that I'm going to have is a 4 pi, and between r and r to the negative 2, I'll take out an r to the negative 2. So factoring that out, 2 pi divided by 4 pi, sorry, that's 2 pi times 2, which is 4 pi divided by 4 pi is 1. R to the 1 divided by r to the negative 2 is r to the 1 take away negative 2 is 3, minus 108 pi divided by 4 pi, 27. R to the negative 2 divided by r to the negative 2 is 1. Okay, so let's simplify this more. So I have 4 pi on top, and then I have a difference of cubes. So I'll just factor that. Cube root of each, r minus 3, and then square the first and last. And then the middle term is negative 3r, so this is the opposite, which is positive 3r. And only the r squared comes down. The 4 pi stays on top. Okay, so now that we've got that, we need to find our critical values. Okay, so this quadratic here cannot be factored, and you can verify with the quadratic formula that it has no real roots. So if it has no real roots, that means it has no critical value. The critical value here is 3, and the critical value here is 0. So it looks like our critical values are 0 and 3. However, within context of the question, a radius of 0 does not make any sense because then we would not have a cylinder. So I only have one critical value, which is 3. So I'm going to set it up as a number line. Now I know I can't go past 0 because I would have a negative radius. So I really have the area to the left of 3, and it has to be above 0, and then the area to the right. Okay, so I just want to do my sign analysis to verify that I actually have a minimum. So I have 4 pi, which is a constant, positive in each. I have r squared, regardless of the value, when you square something, it will be positive. I have r minus 3. R minus 3 is 0 right at 3. The factor is 0. So to the right of 3, the factor is negative. To the left, oh, let me try that again. To the left of the factor, it's negative. To the right, it's positive. And then r squared plus 3r plus 9 is a parabola with no x-intercept, and it opens up, meaning it's always positive. Okay, so looking here, I have one negative, which means it's decreasing. Here I have all positives, which means it's always going to be increasing. So if to the left I'm decreasing and to the right I'm increasing, that means that I have a minimum, and that minimum occurs at r equals 3. Okay, so it says find the dimensions. I found the radius. Now I have to go back up here and find the height. So I'll just replace my radius with 3. And then simplifying, I get 10 over 9. So the dimensions are going to be 3 meters by 10/9 of a meter. And that would give us the least cost. Okay, let's try this one here. I want to find the points on a parabola, and the parabola is 6 minus x squared, that are closest to the point 0, 3. So I want to find the points that are closest to this y-intercept, okay? In other words, closest means I want the minimum distance. Okay, so let's look at the equations that we have. If I want minimum distance, well then I'm going to use the distance formula. Okay, so the distance formula, I want the minimum distance. So the distance formula is the root of x2 minus x1 squared plus y2 minus y1 squared. So I'm finding the distance between these 2 points here. Okay, so simplifying that, it's just going to be the root of x squared plus y minus 3 squared. So since this is the minimum, this means this is my derivative equation, and I'm only allowed one variable. Well, you can see a problem there. I have 2 variables. So that must mean I have another equation, which is my isolating equation. And that equation is right here, the equation of the parabola. So this is my isolating equation. So since y is already isolated, I'm just going to substitute it in here and simplify my derivative equation. Okay, so I have minimum equals the root of x squared plus, instead of y now, I'm going to use 6 minus x squared minus 3 squared. So that's going to be x squared plus, so I have 6 take away 3 is 3 minus x squared. So I can simplify that a little bit more. Just by expanding this, okay? So expanding that, I'm going to have 9 minus 6x squared plus x exponent 4. And then in my last step, I want to group my like terms. So I have x exponent 4, x squared take away 6x squared, and then plus 9. So that is my minimum equation, my derivative equation. It only has one variable, so I am ready to take the first derivative. To help me take the first derivative, I'm going to rewrite this in exponential form. Okay, so let's take the first derivative of our min equation. So 1/2 comes down, decrease my power by 1, and this is an example of the chain rule. So it's the derivative of the outside, keep the inside the same, multiplied by the derivative of the inside. Okay, so let's tidy this up a little bit. So I'm going to have 1/2 times 4x cubed minus 10x all over in the denominator the root of x exponent 4 minus 5x squared plus 9. Okay, so 1/2 of 4x cubed is 2x cubed, and 1/2 of 10x is 5x, all over the root of x exponent 4 minus 5x squared plus 9. Okay, so I'm going to factor the numerator just by taking out a GCF of x, and then I'm left with 2x squared minus 5 all over the square root of x exponent 4 minus 5x squared plus 9. Okay, so in the numerator, I can go a little bit further by just taking the difference of squares and factoring that further. So root 2x minus root 5 times root 2x plus root 5 all over x exponent 4 minus 5x squared plus 9. Okay, in looking at this, I want to come up with my critical values. So that would be in the numerator. So 0, and then this would be root 5 over root 2, which rationalizing my denominator would be root 10 over 2. And this would just be the opposite, which is negative root 10 over 2. Now in the denominator, I can't square root a negative, so this has to be positive. And actually, if you enter this into your calculator, you will see that it has no real roots. So it is a parabola that opens up and it has no x-intercepts. So it has no critical value in the denominator. So that means that I have 3 different critical values that I'm going to put on a number line. Okay. So I'm going to have critical value of negative root 10 over 2, critical value of 0, and critical value of root 10 over 2. Okay, so I'm going to look at my first derivative in factored form. So let's start with x. X is 0 right here. So to the left, the factor will be negative. To the right, the factor will be positive. Then I have this one here. And that factor is 0 when x is root 10 over 2. So to the left, it will be negative. To the right, it will be positive. This factor here is 0 at negative root 10 over 2. So to the left, it's negative. To the right, it is positive. And then my denominator, because it is the principal square root, will always be positive. Okay, so here I have 3 negatives, which is a negative decreasing. 2 negatives make a positive, I'm increasing. I have 1 negative, which is decreasing, and then all positives, which are increasing. Okay, so I'm looking for the points that are the closest. I'm looking for a minimum. So if I decrease here to the left and increase to the right, this is a minimum. Increase and then decrease, this is a max. Decrease and then increase, this is a minimum. Okay, so this means there's a minimum at x equal this and a minimum at x equal to that. So what we need to do is figure out what is the y value that goes with that. So you'll remember from the equation above, my y equals 6 minus x squared. That was the equation of the parabola. Let's figure out what the corresponding y value is. So negative root 10 over 2 squared. So that's just going to be 10 over 4, which is really 5 over 2. So 6 take away 5 over 2. Well, 6 is 12 over 2. Take away 5 over 2 is 7 over 2. Now, because I'm squaring them, they will be symmetrical. So the points that are closest are negative root 10 over 2 and 7/2, and positive root 10 over 2 and 7/2. Those would be the points closest to 0, 3 on that parabola. Okay, so those are 2 examples in part 2. So speaking of parabolas, baby parabolas like to drink the quadratic formula. I would like you guys to do textbook questions, page 188, 9 to 20. Hopefully this video helped, and that's the end of chapter 4.